Acids and bases. There are a number of concepts that were developed for how do you treat an acid and base. I remember even in grade school, we were taught that acids were sour and bases were bitter. But that's only if you can taste them. So I've since learned that that's probably not a good idea unless you're tasting something that's food grade. But in chemistry, you can cook, you just can't lick the spoon. One of the earliest concepts for acids was how does the molecule behave when it's put in solution, in aqueous solution. And Arrhenius developed his concept of an acid and a base based upon how the molecule dissociates in solution. So Arrhenius' idea was that an acid like that, when it goes into solution, it produces hydrogen ions. Just dissociates like that. And that's a pretty good definition. He also said that a base, though, must have an OH group in it. So it makes that polyatomic ion, the OH minus, when it goes into solution. Can you see?
Yeah.
Okay. That was the Arrhenius definition. A problem arose when you investigate the reactions that are involved with acids and bases and found that you could get an acid-base reaction with a base molecule that did not have hydroxyl in its makeup. The classic example of that is ammonia. Right? When ammonia goes into solution, it produces a base. It produces hydroxyls over here. So how does it do that? Let's see. Let me, just in case. Okay, waiting room is closed, so you can come in anytime. Okay. So how do we end up with OH minus when there's no OH in that molecule? Eventually, we discovered that what happens is the ammonia reacts with water, right? Because water is pretty plentiful. Water molecules, there are lots of them, and ammonia reacts with water and produces, it takes this hydrogen ion there and makes a polyatomic out of it and leaves behind an OH. So you get the OH without having one in the molecule itself. So we needed another definition for acid base. And that's where these two scientists, Bronsted and Lowry, came in. They independently came up with this definition. They just said that, okay, an acid, that's good. Acid donates a proton. In other words, it dissociates and makes that proton available. It donates a proton. And a base accepts protons. So they just said, we don't need hydroxyls. Maybe hydroxyls are there, but we don't need them for our definition. We're basing our definition solely upon the proton, the hydrogen ion. So that being said, when you have an acid in aqueous solution, you need something that it can donate to. So Bronsted Lowry says, we're going to donate that proton to water. If that's the only thing in there, the acid and water, it will donate the proton to water. and that'll leave behind that species. Okay, so in the Bronsted-Lowry definition, this is the acid, and this becomes the base. Because according to their definition, the base is the proton acceptor. So if this is an acid, then water has to be a base. And if you have a traditional base in there, then it also reacts with water. Only the water donates a proton, and it ends up here. And that proton comes over here and reacts with this molecule, right? So that proton goes over here, and what does it make? Well, it actually makes a B plus and a water molecule. Okay, or we could say, use a real example. There's our ammonia. Ammonia is a base. So Bronsted-Lowry says it accepts a proton. And it accepts a proton from water and makes this molecule. That's left over. Now this is the base. And what does that make water? Now water is an acid because it donates the proton. Okay, and the Bronsted-Lowry model is the preferred model for all aqueous solutions. We have to go beyond that to work with non-aqueous solutions. But in aqueous solutions, this model works very well. All right. So there we have the Bronsted-Lowry model. There's your acid, there's your base. And this is the pictorial representation, sort of an animation. There's the ammonia molecule, and there's water, and there's your proton that's trying to figure out which way it wants to go. Right, so it could go back and forth. And all these reactions are reversible. In other words, there's equilibrium involved. They can go forward, they can go backwards. And that's what this animation is showing. That hydrogen ion can go over here, or it can go back over there. Now, interestingly enough, if you only have water molecules if it's pure water will react with itself. So in order to explain that, you got two water molecules. That means it's not reacting with itself. It's reacting with a neighbor, but they're the same molecule, same formula. And if you transfer a proton from this one to this one, you get that, and what's left over? That. So that does happen. That makes, let's see, this one accepted the proton, if we keep them in order, and this would be the base, and this would be the acid. Okay? Here we go. Now, when we do these types of reactions, if this is an acid, now it's over here. This one goes over here. This one goes over here. Okay. So this base accepts a proton. Now it has a proton available to donate. That makes it the conjugate acid of this base. And that makes this, strangely enough, the conjugate base of this acid. It just means that it was derived from this acid. Now it becomes a base because it can accept a proton. And if it accepts a proton, it goes back over here. If this one donates that proton, it goes back over here. Okay, in this scenario. You can use other, let's do it for ammonia. Right, so now we have an equilibrium possible. Which one's the acceptor and which one's the donor? This is the donor, makes that the acid. And this becomes the base, the acceptor. Now if we do this, it's accepted a proton. Now this is the conjugate acid. And this is the conjugate base. Okay, it's always that way. When you have an acid and a base reaction, you produce a conjugate base and a conjugate acid every time.
So they just become opposite of what they are.
Yep. This base becomes, now it's able to donate that proton and come back over here. Okay, what is the chemical definition of a strong acid and a weak acid? We think in terms of strong and weak as the ability to corrode. Right? But in chemical definition is not like that. Chemical definition is a strong acid ionizes very far to the right. In other words, that acid wants to give up most, if not all, of its protons. Donates all of them. That's a strong acid. If the concentration is very low, like if we had hydrochloric acid, right, it can donate that proton because it's an acid. Well, this one is a strong acid because it breaks up completely in water. It goes way to this side and produces the hydronium ion plus the chloride ion. So this strong acid says that it's going to be like that and almost none of that. But the concentration could be 1 molar, in which case it would produce a lot of these and be very corrosive. Or it could be 0.0001 molar and produce almost none of that because it starts with almost none and it wouldn't be very corrosive. But by chemical definition, it is a strong acid simply because its equilibrium is far to the right. Weak acids, by comparison, prefer to be far on the left. They want to be over here. And one good example of that is acetic acid. It would produce the hydronium. That's the name of this species. It's the hydronium ion. And it produced acetate ion. But it wants to be over here. And in fact, it's between 10 and 100,000 times more desirable to be over here. Very weak acid for that matter. This is a 5% solution of this vinegar. So you can taste it and it's not corrosive. It doesn't hurt your tongue. But we used concentrated acetic acid in the laboratory. So we buy bottles of the stuff and it's 100% pure. It's called glacial acetic acid. And that stuff is dangerous because it's very corrosive with this high concentration, and it does produce significant amounts of this. And in addition to that, it's an organic molecule. In other words, exposed to air, all it needs is an ignition source and it will burn. And so you never want to store concentrated acetic acid with any oxidizing acids. Just because it says they're acids doesn't mean they're compatible. So you don't store it with nitric acid, you don't store it with sulfuric acid, you don't store it with perchloric acid, right? Because if they get together, they're going to make a mess. Okay. So this is the author's idea of acid strength. Right? Strong acids are mostly over here. Weak acids are mostly over here. And this is also a table straight out of your textbook. What's the K value? Right? If we look at this in terms of K, we would say if we wrote the K for this, then this one would have a very small K. It would be on this side, right? Because this value is in the denominator. Concentrations here in the denominator, these are in the numerator, very small. So the K would be very small for this acid. For strong acid, the K is very large. In fact, it's virtually infinity. Divide by 0, right? Because there's nothing left over here. I accidentally pushed that button. Okay. The strong acids are very easy to deal with when you're doing calculations, because you don't have to worry about equilibrium. If you know the concentration, the original concentration of the acid that you put in solution, that's the concentration of the hydrogen ions. Okay. By comparison to water, a strong acid is a much weaker base. Now, when we speak of strong acid and weak acid, we can also speak of strong base and weak base. In terms of Bronsted Lowry, a strong base is a strong acceptor of protons. So it really wants to latch on to protons. And hydroxyl is a good example of that. When water goes through that reaction with itself, it produces hydroxyls, but it really wants to be water, H2O. So its desire to be way over here means that if it produces hydroxyl over here, then that hydroxyl is extremely attractive to protons. It's a strong base. A weak base would be one that doesn't care. I mean, it doesn't want protons at all. And this would be an example of it. No. I'm sorry. That's strong. That's a strong base. Excuse me. This is the acid. This is the conjugate base. If this is a weak acid, then it does want protons very badly. It wants to be over here. The better example here, this one again, wants to be like that. So it's going to have hydronium plus chloride. Okay. If it's a strong acid, it produces this conjugate base. And if it's a strong acid, it wants to get rid of that proton. So it wants to be way over here. That means this doesn't want the proton back. Right? It got rid of it already. It doesn't want it back. So that means if this is a strong acid, that's a weak base. And if this is a weak acid, that's a strong base. Okay, it's all based upon equilibrium. All right. What I demonstrated earlier was a self-ionization. Self-ionization can happen with any compound. In other words, this is water that self-ionizes. And I showed you that example on the board, where it just transfers a proton over to this one. Now you got the hydronium ion plus the hydroxide. But you can do it with pure ammonia too, right? farmer goes out in the field with his big stainless steel tank pulling behind his tractor, and it feeds his injectors. And it just feeds that pure anhydrous ammonia into the ground with the injectors. Well, inside that tank, these reactions are going on, right? One ammonia is transferring a proton to another ammonia and making this ammonium ion plus this NH minus because it lost a proton. And both of these reactions, any of these reactions that involve self-ionization or auto-ionization, you can write an equilibrium expression for it. And it's quantitative, there's a value, a K value associated with any of these reactions. This one's the most important one. Because we're studying acids and bases in aqueous solution, we need to know how water behaves. And we're going to not just dip our toes in that pool, we're going to jump in head first. Okay, this auto-ionization of water we refer to as amphoteric nature. What that means is water can behave as either an acid or a base. Now it's fairly straightforward when you look at it in these terms, right? One's an acid, one's a base. But when water is presented with what we would normally consider a true acid or a true base, how does it behave? Right? Well, they're competing reactions. Water can either react with the acid and base that we introduce, or it can react with other water molecules. And all of those reactions are going on at the same time, all the time. Just because you put an acid in water, like hydrochloric acid or acetic acid, doesn't mean that it stops reacting with itself. It still reacts with itself. And the rules for writing a K value for acids, or bases for that matter, still apply. If there's a solid produced, if there's a solid involved, or if there's a pure liquid involved, those do not become part of the equilibrium expression, right? So when we write this one, where you have water reacting with itself, these are pure liquids. And they produce hydronium plus hydroxide. These are in aqueous solution. So these are the only ones that have valid concentrations that we can use in an equilibrium expression. So if we wrote the equilibrium expression with these concentrations in the numerator and these in the denominator, these would go away anyhow because they're pure liquids. They're not included. So that's why the Ka for this reaction, and we give it a special designation, Kw, is equal to the concentration of this one times the concentration of that. Okay. Now notice they've got it written here as just hydrogen ions and hydroxyls. That's a matter of convenience. This is actually what happens. In aqueous solution, you never have free protons. Protons are transferred from one place to another. Right? They're never free. But for convenience sake, what we're saying is water can self-ionize and produce hydrogen ions and hydroxyls. And that's where this expression comes from. It means exactly the same thing as this one. It's just more convenient to write it this way. Okay? So when you see it that way, it means that. And the K value for this reaction at 25 degrees Celsius is 1 times 10 to the minus 14. So that tells you that it doesn't produce much of this at all because it's very small. These are products, right? If that's a small value, the products are almost non-existent. They're there, in very small amounts. So we have three possible scenarios that we look at concentrations. And before I get into those, look at it this way. In this reaction, when you produce these products, where did they come from? They came from water molecules, right? So if you produce a certain concentration of this one, you're going to produce exactly the same concentration of that one, because there's nothing else in there but water, right? So if you transfer a proton from one to the other one, you have created this one and this one out of the same molecules, out of the same source. So if we have a value here, how did we get that value? In pure water, it would have to be, that's the only way that both of them can be equal and produce 10 to the minus 14. 10 to the minus 7 of this, 10 to the minus 7 of that, gives 10 to the minus 14. Okay. Now, in pure water, that's known as neutral. Or in any other solution, if you have equal amounts of hydronium and hydroxyls, you have a neutral solution. In water, their concentrations will be this. If the concentration of this one exceeds that one, they still have to equal to this value, right? Because this reaction is going on all the time. Whatever you do to that solution, if you unbalance it toward the hydronium, say -6 here, that one has to be -8 to give you this equilibrium constant. Okay? And in that case, this would be acid. When you have a higher concentration of hydroniums or hydrogen ions than you do hydroxyls, then you have an acidic solution. And you can taste it if it's not particularly hazardous. You can taste it. I wouldn't want to taste a solution of hydrogen cyanide, right? That could be deadly.
Sounds awful.
But it would taste acidic right before it killed you. And the other way around, if we change, say this one to 8, this one would have to be 6. And in that case, this concentration is greater than that one. Right? In that case, you have a base or a basic solution. Okay? All right. I've introduced this topic already. Acid base, conjugate acid, conjugate base. In order to identify a conjugate acid or a conjugate base, you can only transfer one proton at a time. If you transfer more than one proton in a reaction, then it may be a valid overall reaction, right? But it does not give you the conjugate acid, conjugate base that you're looking for. So, for example, if we have sulfuric acid, it's an aqueous solution, it will be in equilibrium. Well, actually, it's a strong acid for the first proton. But for the sake of argument, this is our acid. That means this has to be the base. And what do you get when you transfer one proton? What's left over here? HSO4 minus. Because we transferred a proton to this one. So this is the conjugate base of that acid, and this is the conjugate acid of that base. You can only say this is a conjugate base if you transfer one proton. Right, we've got another proton here. If we wrote it like this, and said this was the overall reaction, then we would have to balance our equation. We need two of these. Okay. Well, that's a valid equation. It does not tell us the conjugate acid, conjugate base, right? Because you transfer two protons. The way we get to this one is actually we take that one, transfer the second proton here, makes that one that one. Now this becomes the acid for this reaction. That's still a base. This is the conjugate base for that acid, and this is the conjugate acid. Okay, one proton at a time. And for this one, there's an equilibrium expression for that one. Right? So we write that Ka would be this conjugate base. I'm going to abbreviate the other one. Just put that proton in there. And this is H2SO4. That would be the Ka for that acid reaction, acid-base reaction. Actually, it's the dissociation constant for the Ka. And this one, this would be 1, this would be 2 for the second proton. Now we have this one, SO4, 2 minus, another proton, and then the acid that it came from. Okay? So each one of these reactions has a different K value. Okay, if the equilibrium lies far to the right, the Ka should be very large, greater than 1. Just like any of our equilibrium expressions. If the equilibrium lies to the left, it's a weak acid, the K should be very small. All right. So in this generic reaction, where we're going to acid combined with water to make our conjugate acid and our conjugate base. If water is a better base than A minus, do products or reactants dominate? Think of it in these terms. When we're trying to compare bases, which one has a stronger attraction for protons? Okay. The stronger base comes from the weaker acid. If water is a better base than A minus, if water wants protons more strongly than A minus does, then it wants to be over here. Okay. So the reactants would dominate in this. Do products or reactants dominate? Water is a better base than A minus. Water's a better base. It wants to, that doesn't make any sense. If water's a better base than A minus, our competition here is between which one wants the proton. This one wants the proton more. If this is a stronger base, it means a weaker acid. Oh, okay, I see. If water is a better base, in other words, it wants the proton very bad, then it's going to accept the proton more strongly on this side than this one will accept the proton on that side. Okay, so that's why the products dominate in this reaction. That means that HA is a strong acid. because it makes a weak base. This base is weaker than water. How about the value? The value of Ka is greater than 1. It goes that side more strongly. All right. So consider a 1 molar solution of HCl. Order the following from strongest to weakest base and explain. Okay, we're starting off with a 1 molar concentration of HCl. And that may not be significant. Strongest to weakest base. All right, this is going to produce a very weak base because that's a strong acid. This is very weak. Okay. What's our other choices? Strongest to weakest base. For this one, we're going to produce hydrogen ions plus hydroxyls. This is a very weak acid that dissociated this way. So if this is a weak acid, this is a very strong base. Okay. How about chloride? Well, we decided chloride. Chloride is a very weak base. This is a very strong base. And A minus from a weak acid. So this is our generic acid that's weak acid. That's producing that and that from a weak acid. So that means this is a strong base. So if we're going to order from strongest to weakest base, which is the strongest base? Well, more than likely, this one's the strongest base. Most weak acids produce, most weak acids are stronger acids than water. Now, there are some exceptions, so we have to make some assumptions here. And I'm going to say that this one is the strongest base. It's a stronger base than this one, which is a stronger base than that one. Oh, we're going to go through a process here. I didn't notice that. How good is the chloride as a base? Not very good. Is A minus a good base? Well, yeah, it's a pretty strong base. Wait a minute. Oh, I'm sorry. All right. We're ordering this one and this one and this one. Okay. This is a weak acid. So what kind of base is it? Well, if we look at it in these terms, where water is reacting with itself, it's just as good an acid as it is a base, it's a weak base. So this is a very weak base, but this is an even weaker base. But this is a strong base. So it should be this one first, and then it should be this one next, and then that one, I think. No, I got them turned around. Why is this one a stronger base than that one is? Oh, yeah, okay. This is a strong acid, so this is a very, very weak base. Okay. Yeah, that makes sense. So what we're saying is the strength of attraction to protons is the strongest for this one, and the very weakest for that one. The water's in the middle. Did I confuse you? I almost confused myself. Yeah. I think we'll have a better understanding once we start working with real problems. This introductory material can get kind of squirrely. Okay, now suppose instead of putting the base in solution, we put the salt of the base. So that brings me to the definition of, for acid-base reactions, when you have an acid reacting with a base, and this would be an radius base, you get this anion and that cation combining. Right? This is a cation, this is an anion. And then this hydrogen combines with that hydroxyl to make water. Okay, that's the generic acid-base reaction. So this is your acid. Obviously, this is the base. This is a salt, and that's water. That's the way all acid-base reactions go, as long as there's a hydroxyl in here. Without that, we have to modify the theory a little bit. But this is the definition of a salt. It's the consequence of an acid and a base reacting together, produces a salt. So here we have a salt, sodium combined with some anion, A. So if we make this one sodium, that's what you get. Okay? So now, if we put that in solution, not any of these, but just take that and put it in solution, what happens? Well, if this is a weak acid, this is a strong base. Okay. Now we're going to combine this one. We're going to say something about the solution when we know these facts. If this is a weak acid, it means this is a strong base. Okay? And what does sodium do? When we put this in solution, it breaks up into that plus that. And what does sodium do? Nothing. It's a spectator. Sodium doesn't react with anything. Once you put it in solution, we get this produced. Okay? When we put that in solution, now this is a strong base. We just determined that. That is a strong base, which means it goes for protons. So this is the reaction you'll see. If you put this in solution, and A is an anion from a weak acid, means it's a strong base. This is a strong base, and it takes protons from that acid very easily. It goes for those protons, which means you produce a conjugate acid and a conjugate base, the hydroxyl. Now, which side of this equilibrium is it going to be on? Mostly. If this is a strong base, it's going for that proton. It's driving the reaction way over here. So this equilibrium is going to lie far to the right. No, wrong. That was the inherited slide, so I just decided I would make a statement and say, no, the authors are wrong. It's far to the right. That's why when you put, say, sodium acetate, right? Sodium comes from sodium hydroxide, which is a strong base. And acetate comes from acetic acid, which is a weak acid, makes it a strong base. So this anion, that's a very strong base once you put it in solution. So if we do that, then it's going to latch onto protons from water molecules and drive the reaction to the right. That's why this salt solution, this in solution, is basic. For that reason, because this is a strong base, it takes protons from water and leaves behind hydroxyls, which determines its basic nature. So it makes a basic solution when you dissolve the salt of a strong base in a weak acid. Sorry. Okay. Let's see. Is the value of Kb greater than or less than 1? Okay, now we have to define what's Kb. Right? So when you put this salt in solution, sodium's a spectator, and the reaction is our A plus water yields HA plus OH. Right? So this is a liquid. These have concentrations. So the Kb for this reaction is equal to this equilibrium concentration, that equilibrium concentration, divided by this equilibrium concentration. Okay? So if we're in the same scenario, right? This is a very strong base. That's a very strong base. So it's going to drive the reaction way to the right. That means the Kb is going to be very large, greater than 1. Okay. Does this mean A minus is a strong or a weak base? Well, it has to be a strong base. Okay, we've already determined it's a strong base. But if the Kb is very large, that means A minus has to be a strong base. All right. Acetic acid we've looked at, and HCN, hydrocyanic acid. These are in an aqueous solution. They're both weak acids. Acetic acid is a stronger acid than HCN, which means what? If it's a stronger acid than hydrocyanic, it produces a weaker base. So C2H3O2 minus is a weaker base than CN minus. If we put HCN in solution, it's going to produce that. If we put acetic acid in solution, it's going to produce this. If this is a stronger acid than that one, that means it produces a weaker base. Okay. So arrange these bases from weakest to strongest. All right, we've got another reaction going on in here. Right? So they want us to arrange this one, oh, sorry, this one, and this one, weakest to strongest base. Okay. Arrange those in order of weakest to strongest base. So we have to say, all right, which one is the strongest acid? This is the strongest acid. So this would be the weakest base. You know that one. That's the weakest. What's the strongest base? Oops. There. The strongest base has the strongest attraction for protons. This is going to be the weakest acid. So that means it's the strongest base. Okay. This is going to be slightly weaker base than that one. And this one is going to be the very strongest, maybe not. It depends on the K values for this one and that one. This K is 1 times 10 to the minus 14. What's the K for this one? I know the K for that one is much, much smaller. So this is the strongest base. This is the next strongest base. So it'll be from weakest to strongest. Okay, weakest base is this one. And the next, and the strongest base is that one. Now we have to order these two. Right? This is a stronger base than that because it's a weaker acid. And then that would put this one here. Let's see if I did that right.
No.
Well, it's not going to tell us.
Go to the next one. Look.
Oh, okay. Oh, water. Okay. That's true. It just didn't answer the question. Okay, is water a stronger base than this one?
No.
No, right. It's less than that one, so it should go right in here. That makes sense. I put this one on that side, but the conjugate should go on this side. I think it'll make a whole lot more sense once we work some problems. I think the authors are fond of these types of scenarios. Most trained chemists are like that. They shy away from working actual problems when they can. Speak in generalities. I think it makes more sense to solve problems. Discuss whether the value of K for the reaction is greater than 1, less than 1, or equal to 1. Okay, Ka for this reaction is that, Ka for this reaction is that. Explain your answer. Okay, so here's what we've got going for us. The Ka for this reaction. Notice that we're reacting this acid with a conjugate base of HF. Okay. So we want to know which side is it on. Does it go to this side or does it go to that side? So the Ka for this one is 6.2 times 10 to the minus 10. And that means, and HF is 10 to the minus 4. So this one prefers this side, and that one prefers that side. But which one prefers stronger? I think this one prefers stronger there because it's 10 to the minus 10. So it prefers to stay on this side. And that means that the K should be less than 1. And I'll see if what does each K mean? All right. Ka for HCN is very small. Strong drive to remain this side. That's true. Ka for HF is small. Strong drive to remain HF. I said that already. The comparison will break the tie. Ka for HCN is much, much less than Ka for HF. So HCN wins, driving the reaction toward HCN, right? So the reactants are favored, which makes the K, the combined K, smaller than 1. Okay. Calculate Kb when you know Ka. All right. Sometimes you do need to know what Kb is for a reaction. If you say you have, let's use acetic acid again. And the K for that was, what was that? 6.2, no, I'm sorry, I'm looking at the wrong one. Here it is, 1.8 times 10 to the minus 5. Okay, now we can go back. Excuse me, wrong direction. Okay. So if this is the Ka, what's the Kb for this? Not for this reaction. We're not going to say we're going in reverse here because this reacts that one with hydrogen ions, right? So the reverse would be just like when we learned Hess's law, you would just take the inverse of this if you're going backwards. But we're not going backwards. Kb means we're reacting this with water. And now we're going to have this one. That's the Kb. What's the Kb for that reaction? Okay, we're gonna work this from a generic standpoint to begin with. Ha is our acid. We're going to make A minus and H plus. So there's A minus and there's H plus. So that's the Ka for that reaction, right? There's the A minus, H plus, and there's the acid. And this is for weak acids. Right? Strong acids, it has no meaning because they completely dissociate. Right? So when we take that A minus and react it with water, like this one, we get that acid back plus OH minus. So the Kb expression for this one is like that. Right? The acid and the hydroxyl divided by the conjugate base of the acid. And notice they're not opposites of one another. I mean, you can't just flip one and get the other one. So there's something else going on in here. We have to introduce the reaction of water with itself. So when you add these two together, right? Actually, we don't have to introduce water yet. When you add these two together, like we do, what we would do with Hess's law, actually a modification of Hess's law, then the A minuses and the HAs cancel, and we end up with the K for water. So here's the Kw for water there. But that is equal to this one times that one. That square in there is an artifact. It should have been times. So Ka times Kb equals Kw, because Kw is the expression for this one. But it's a combination of these two, which is Ka times Kb. Remember the equilibrium constants of a combined equations, you multiply them together. So when we multiply these together, we get Kw. There's your expression. So Ka times Kb equals Kw. If we solve for Kb, that gives us Kw divided by Ka. So if we divide Ka into 10 to the minus 14, we'll get the Kb for this reaction. So for this reaction, that would be 1.8 times 10 to the minus 5 is Ka. And we divide that into 1 times 10 to the minus 14. Okay. Let me do that real quick. So Kb for the acetate ion is is 5.6 times 10 to the minus 10. That's equal to Kb for this reaction right here. And you can do the same thing for Ka. If you know Kb, then you say, all right, Ka is going to be this part reacting with water and dissociating. Okay, what's the value of K for this reaction? Well, we need two. We're going to use Hess's law again. Right? HCN yields H plus and Cn minus. So that would be this one to that one. And there's a hydrogen ion involved in there. Okay. And the one for this one, HF yields H plus plus F minus, only that was the wrong direction. Right? We need to have F minus on this side. So that's the expression for this one. This is the expression for that one, but we need it the other way around. We actually need the Kb. Actually, no, we don't. No, we do need the inverse for this one. Right? Because if we flip that one around, that puts F minus and HF on the correct side. Okay, so we don't have to do Kb for this one. We can just invert the equation. And that gives us 1.4 times 10 to the minus 3, 10 to the third. So now, if we combine those two equations, see, I think I'm going to put them up here like that. Combine the two equations, the H's cancel. And then we just multiply this one times that one, and we get the answer to our reaction. 8.6 times 10 to the minus 7 is the K for this reaction. If you have a solution with hydrocyanic acid and fluoride ions, how do you get the fluoride ions in there? We put them in there as a salt, like sodium fluoride. Sodium is a spectator. It's not involved in the reaction. So this one plus that one yields these two. And on this side, you'd have sodium cyanide in solution. Okay, pH. What do we mean by pH? There was I think it was Danish, under the name of Sorensen. He was either Danish or Swedish. And he was working with acid-base reactions, but he wearied at using scientific notation and actual concentrations of hydrogen ions. So he said, I need a system that is more wieldy. So I said, I'm just going to do a mathematical transformation. I'm going to take this big number here, the scientific notation number, and I'm going to take the log of it. Okay. So, for example, if we had hydrogen ion concentrations in the solution were 1 times 10 to the minus 6 molar. What happens when you take the log of that? Well, the log of 1 is 0. Yeah, that's right, 0. Plus the log of 10 to the minus 6, which is what? Minus 6? Take the log of that, and that's base 10. So the log of that would be 6. All right, remember the definitions of log? Log of x equals y means, and that's base 10, is 10 to the y equals X. Y is the power of 10 that equals X. So that means this value is -6. But he says, I don't want to use minus numbers either. So it said, I'm just going to say, and that's equal to pH. Small p, big H. Okay, that was Sorensen's solution to the problem. But we have to understand that if we've got a continuum here, right, and our neutral solution is what? Hydrogen ions equal 10 to the -7. Remember earlier, 10 to the -7 is neutral. Okay, what would be the pH of that? 7. Negative log of this value is 7. Okay, so what if we have a higher hydrogen ion concentration? So we have a 10 to the -6. What would be the pH? 6. And it just goes, okay. As you increase the hydrogen ion concentration, the pH value gets lower. So a smaller value of pH means more acidic. And go the other direction. Yeah. We usually don't go below 12 or greater than 12. These are basic pHs. These are acidic pHs. Okay, these are some examples of stuff. Like 1 molar sodium hydroxide is obviously very, very high pH. And 1 molar hydrochloric acid is very low pH. Yeah, milk is slightly acidic. Not too bad, just slightly acidic. Black coffee is more acidic. Vinegar is about 3. Lemon juice is more acidic. Stomach acid is between 1 and 2, depending on the meal, because your stomach will respond to eating. The battery acid is about 1. Battery acid is sulfuric acid.
I think that seems crazy because it says seawater is kind of basic and milk is kind of acidic.
Yeah, seawater is basic. It's got all those cations in it: sodium, potassium, calcium, magnesium. It makes for a basic solution. And that's the problem with coral reefs. They can't extract calcium from seawater under acidic conditions.
So that's what it is.
So when you acidify the ocean, the coral reefs die.
Did you see where they're making new starts for coral reefs using like people's ashes? Like you can be cremated and they'll put your ashes into these. It's like it's kind of round, dome-ish looking, and has holes in it for the animals to gravitate towards and build on and everything, so they can help with coral reefs.
Okay.
I thought it was cool, but it's kind of scary. It's kind of weird.
But one of the takeaways here, besides the fact that you see can relate to real world substances, is to understand that pH is just a mathematical calculation. If you have a value of, let's see, use an example. Well, 1 molar HCl. 1 molar. The negative log of 1 molar is what? 10 to the what is 1? 10 to the -1, the log, let's see. What's the log of 1? log of 1 is -1, isn't it? No, that's 0. Log of 0. -1. Okay. Yeah. So log of 1 is 0. And -0 is 0. So 1 molar HCl, actually that should be right down here on 0. Suppose we have 2 molar. What power of 10 will give you 2? Is 0.3. So this is log of this is positive 0.3. So we take the negative of that, negative 0.3 pH. For that hydrochloric acid concentration, right? The point is that you can get negative pHs. That's just, they're not very useful. Okay. Sorensen was interested in systems that remained within positive range. So he was working with living systems. The point is, it's simply a mathematical transformation. How about 10 to the -4th molar hydrogen ions? What's the pH of that one? Yep. That would be 4. How about this one? 4 times 10 to the -2, correct? 4 times 10 to the -2. Hydroxyls.
How do you know it's -2?
I just moved it over here.
Oh.
I converted it to scientific notation. What's the pH of that one? Well, what you can do is, there are 2 ways to do this. Find out what the hydrogen ion concentration is for this solution. The way you do that is, you say hydrogen ions times hydroxyls equals Kw, which equals 10 to the -14, correct? So if you know this one, 0.040, you can solve for this one. You just divide that one by this one. 10 to the -14 divided by 0.04. Which is 2.5 times 10 to the -13. Okay, then you can take the negative log of that. So the log is -1.26, so pH would be +1.26. Okay. Oh, excuse me. Nope, I do that all the time. My calculator spits it out in scientific notation, and I don't take account of that. 12.6. Didn't look right anyway. So that's one way to do it. Convert it to hydrogen ions and then do the transformation. The other way, I think I've got slides on that. We'll get to that in just a second. What if you know the pH and you want to go backwards? You need to know the hydrogen ion concentration. You just use the definition. Equals 5.85. Okay, solve that equation. You got to get that negative out of here. You can't do the anti-log with the negative on this side. So you have to say the log of the hydrogen ion concentration is equal to -5.85. Then you can do the anti-log. And when you calculate it, the anti-log of this number is 10 to the x equals, well, actually, it's hydrogen ion concentration is equal to the anti-log of negative 5.85. And that's equal to 10 to the minus 5.85 on your calculator. There you go. 1.4 times 10 to the minus 6. Now, okay, now we're going to get to the quicker way. Like I said, pH is a mathematical transformation, nothing more. So we can also do pOH. If you know the OH concentration, you can just do the negative log of that value and you have pOH. Okay. So we're going to go back to what's the KW for water, right? Hydrogen ion hydroxyl equals 10 to the minus 14. Then we're going to take the negative log of that entire equation. And how do you do that? Mathematically speaking, this is this term times that term. So that means when you take the log of these two, when you take the log of a product, you get the summation of those logs. Right? So that's why it's the log of this one plus the log of that one. That's the nature of logs. Remember that from algebra? Yeah, that's why it's a negative here, because we're taking the negative log of that one, the negative log of this one, plus the negative log of that one. Okay? So if we do that, and we take the negative log of this one, the negative log of that one, and the negative log of that one, right? Because what I showed you earlier, they come from the same place, so these concentrations have to be equal if it's a neutral solution. So what's the negative log of that value? 14, right? 14. The negative log of this value is 7. Negative log of that one is 7. And this is also pH, and that's pOH. So pKW, right? The same transformation of the K value, pKW is equal to pH plus pOH. So that makes things a whole lot simpler. If you know the pKW is 14, and you can calculate the pOH, so we can take that value of, what was it, 0.040, just take the negative log of that, and that's equal to 0.040 is 1.40, rounded off. Now the pKW is 14, and that's equal to pH plus 1.4, right? So now the pH is equal to 14 minus 1.4, which is 12.6. So we got the same answer, but it's a lot easier. Oh, we want the pOH of this one. All right. So this one is pH is 4. So the pH in that one would be 4 plus the pOH. Now the pOH is equal to 10. 14 minus 4. How about this one? pOH of this one is just a negative log of that value. We did that one already, 1.4. Okay. All right. What's the OH concentration for this solution? Well, we've got the pH here. So if we subtract that from 14 and then take the negative log, we get that value. Okay, do we need to do that? I can't. So our pH is 5.85. Okay, and we're looking for the PM, we're looking for the hydroxyl concentration. That's our end game. So if we take this one, POH is equal to 14 minus 5.85, which is equal to what? Let's see, 5 on 8. Nope. Yeah. 10 carried to 1, 10, 14, that's right. 8.15 is POH. POH is the negative log of the hydroxyl ion concentration. So negative 8.15 is equal to the log of OH. And the anti-log of minus 8.15 is equal to hydroxyl ion concentration. And that's this value. Okay. All right. So we're going to have acid-base problems of various types. We need a method for solving these problems. What you want to do when you confronted with an acid-base reaction and questions involving that reaction is, first of all, what are the major species in the solution? Identify those species, because those are going to be competing reactions. You've got these species, what are they going to react with? What are they going to produce? Because we need to identify the major reaction in order to answer most questions. What's the dominant reaction that takes place then? Is it an equilibrium reaction? Or is it essentially one that goes to completion? Right? If it's an equilibrium reaction, then we know that we're probably going to set up an ice table and use the equilibrium expression. If it essentially goes to completion, then all you need to do is calculate the stoichiometry for the problem. What's it going to end up? And just a heads up, some solutions are better solved first by assuming going to completion. And then you take the completed reaction and you work backwards to equilibrium. Okay, we'll do something like that. All right, so consider this reaction. 2 times 10 to the minus third molar HCl. What are the major species? All right, we know we're going to have hydrogen ions, chloride ions, and water. We're not going to have any HCl at all because it's a strong acid. Okay. What's the pH? Well, if we know that these are the major species, then we just need to say, what is this value right here? Well, it's going to be equal numerically to that one. This is the reaction that goes to completion. So now all we have to do is take the negative log of this value, and that gives us the pH, 2.7. How about the pH of this one? It's a lot lower concentration, about 8 orders of magnitude diluted. All right, we have major species of this one, that one. HCl doesn't remain. All right, so then if we take this value and calculate the pH, we find that it's 10.8, which is what? That's basic. Right? When nitric acid is added to water, or hydrogen nitrate is added to water, then it becomes nitric acid. This reaction immediately takes place. Nitric acid plus water yields hydronium ion plus nitrate ion. Going to completion. Why is this one not reaction not likely? Well, because if the HCNO3 is a strong acid, this is a very weak base. It has no interest in taking protons from water. This reaction, like I said before, this reaction is always happening in water. Is water the major contributor of hydrogen ions? No, actually it's these right here. Those are the major contributors. Okay, so if we have a concentration of 10 to the minus 2 molar HNO3, major species are these, none of that left over. So we calculate the pH based upon this value going to completion. Then my introductory chemistry course. That's where we stop. We don't do equilibrium reactions and acid bases for the intro class. But in this case, we're going to look at weak acid equilibrium problems. In fact, they're more interesting anyway. We need to know the major species. Now, a weak acid is definitely an equilibrium problem. So you choose the species that can produce hydrogen ions and write the balanced equations for the reactions that produce those hydrogen ions. Then you look at the equilibrium, look at those reactions in terms of their equilibrium expressions and decide which one will be dominant in producing hydrogen ions, because that's the one that will determine the pH. This comes from the authors, and it doesn't talk about ice tables. It just assumes that you know what to do. I think the use of ice tables in this situation is a better way to keep you out of trouble, because then it focuses your attention on what the actual expression for the equilibrium is. So that's what we're going to do. All right. Consider a 0.8 molar aqueous solution of weak acid, HCN. HCN, and we've got 0.8 molar. And the K value for this reaction is equal to 6.2 times 10 to the minus 10. Okay, what are the major species in solution? Well, what is this reaction? It's going to react with water. It's going to produce hydronium ions plus Cn minus. The major species in this reaction are these two. These are not major species because that value is so small. So what reaction do we have? Well, we've got this reaction. These are the major species. And there's your Ka. You know. You've also got a competing reaction of water. And the K for that value is 1 times 10 to the minus 14. Okay, why did I bother putting that one up here? Because this one happens in the aqueous solution all the time. It's always there. You can't get away from it. You have to consider it. All right, which reaction controls the pH? Which one produces hydrogen ions or hydronium ions? is the major source. This one, right? Because that value is larger. Right? So this one controls the pH. All right, now we know which one to use to calculate the pH. Oh, that's as far as we're going with that one. So I thought we were going to do something with it. Okay, maybe we'll come back to it. That one always catches me off guard, and I've done the slide set many times. It always sneaks up on me. How about we calculate the pH of 0.5 molar aqueous solution of HF? HF is a weak acid. Even though fluorine is a halogen, and hydrochloric acid and hydrobromic acid and hydroiodic acid, those are all strong acids. HF is a weak acid. And it's a weak acid for two reasons. One is fluorine may be the most electronegative atom in the periodic table. And it wants to draw electrons to itself, which theoretically would free up the hydrogen ion. But when it does that, when it makes that choice, it makes this very strong negative, almost ion. Strong negative, and this is a strong positive. Then the electrostatic force holds them together. Plus, this is a very small ion, which means the charge density is very high. Whatever charge it's trying to develop, it's not a complete charge, but it's close. Whatever charge it's trying to develop is concentrated in a small area, which makes it very strong. It's a strong electrical field, which draws that hydrogen ion very close to itself and doesn't want to let it go. So that makes HF a weak acid. Now you can still get the hydrogen loose, but not much. It's 10 to the minus fourth, which is actually a stronger acid than acetic acid. But that being said, calculate the pH of this solution of the weak acid. All right, so we go through, look for the major species, right? Major species are HF and water. Okay, so our competing reactions are HF plus water yields this, and water plus water yields that. So which one's the major? Obviously this one. Right? It's much stronger acid than that one. So we focus our attention on the HF. So here's the reaction that it'll undergo. HF plus water yields hydronium plus F minus. We set up our ice table. So here's the initial condition. We start off with that concentration right there. And there's none of this and none of that. This is approximate. The reason we say approximate is because actually that one should be zero, not approximate. This is approximate because you still have some hydronium in there from self-ionization of water, but it's not significant. Okay, so a change, we're going to lose some of this, and we're going to make some of that and some of that. So our equilibrium situation is X and 0.5 minus X. Okay, so now this is our equilibrium expression. Hydrogen ions, fluoride ions, and HF is equal to that expression. We plug these values in. That one goes in here. Those two go over here. Right? So now we have our expression, our equilibrium expression here. We have to make a decision. If we keep that X, then we're going to have to solve a quadratic equation. Right? But we can also assume that since this is a very weak acid, that X is going to be very small in relationship to 0.5. If this value were extremely small, like 0.0001, then we would have to keep the X because it would be just way too big compared to that other one. But this is very, very small compared to that one, and we just drop it. We keep these two, of course. And then we have an expression where X squared equals 7.2 times 10 to the minus 4 times 0.5. So that's twice this value. 0.5 over here becomes 2 over there times that. And then we take the square root of both sides, and that gives us X. So X is our hydrogen ion concentration. The question was pH. So now if we just do the transformation, we get 1.72. Now the rule, just like any of our other estimates from equilibrium, the rule is this within 5% of the value if we did the quadratic? And the way you do that is you take this value right here and you plug it in there, there, there. And what value do you get? Right. It should be very close to this one, the K value. If you plug in this value here and here and here, do the calculation, it should be within 5% of that one. And if we did that, we find that it is. So it's less than 5% error, then we go with it. Oh, okay. I forgot to add this slide. This is actually where we're going to do the calculation. So we plug in that value. Let's see, back up. Yeah, 1.897 times 10 to the minus 2 is X. So if we put it in here for each of the X's, here, 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 do the calculation, we get 7.81 times 10 to the minus 4 as compared to the K value that we know to be 7.2. So this is the calculated K with our determined X value. And we compare that to this one. Is it within 5%? Right? Well, we just say this subtract the known value divided by the known value times 100, and it's 3.9%. So we're good. Okay, here's another concept that might twist your head around. It's called percent dissociation, or sometimes it's named percent ionization. All that means is if we have an initial concentration of our acid, and we determine that the amount of the acid that was dissociated in the process is a value, then the ratio of those two times 100 is the percent dissociation. But another way of looking at that is, if we start off with 1 molar acid, and it produces 0.05 molar of the hydrogen ions and 0.05 molar of the conjugate base, then we would take 0.05 divided by 1 times 100. And that's 5%, right? That's 5% dissociated. That's what that means. We look at what we end up with over here versus what we started with. And that's the percent dissociation. Strangely enough, the percent dissociation of weak acid increases as the concentration goes down. Okay, so if we started off with a 1 molar and it got 5%, then if we went to 0.1 molar, then this might be, well, I don't know, 7 or 8%. But what does that mean? Well, it means, yeah, the percent dissociation was greater, but what about the concentration? Well, you only start with 0.1, so the concentration can't be as high. Right? Maybe it's 0.008 molar hydrogen ions. That'd be right. 0.008 divided by 0.1 is 0.08 times 100 would be 8%. Okay. So in that case, the concentration here is less than that, but the calculated value of dissociation is higher. Okay, that's all that means. Okay, we're going to come back to that in a minute. In fact, it's going to be part of working problems. In fact, I'm going to do it right now. If a solution of 8 molar formic acid, HCHO2, formic acid, that is the simplest carboxylic acid in the organic world. And it's called formic acid because it's derived from the name for ants. The genera of ants is I can't remember what it's called, but this refers to ants because formic acid is one of the part of the mixture that they inject when they bite you, and that's why it burns. Okay, fire ants are really bad for this. Fire ants have that plus some other things that potentiate your nerve endings. But formic acid is like that. So there's your acidic proton. This is the one that dissociates in water. Okay. So here's the anion, the formate anion that forms when one proton dissociates from it. If we start off, this is our ice table. We start off with 8 molar, then we have none of this and none of that. And if we say that the dissociation is 0.47%, which means if we start off with 8 molar, we're going to end up with hydrogen ions that are 0.47% of that value. And here I've used the decimal equivalent of percent. So you just divide this by 100 and you get this fraction. Okay. So when we multiply that times this, we get that value. 3.76 times 10 to the minus 2. Right. So that's how much we end up with here of hydrogen ions and formate ions. And then this value is whatever required transformation. Acid-base reactions like this are easy to work with because you only get one proton and one conjugate base out of this reaction. Even if there are multiple protons here, you do these one at a time. So this is always X, X, and this is concentration minus X. That's why the authors didn't go into this detail in their set of rules, because it's simple. Right? They're assuming that you've already had an equilibrium and you know how to do this, but I think it's important to work problems this way, simply because we're going to use this information in some shortcut methods later. So if we stick to this process, I think it's easier to make the transition when we start talking about buffers, in other words. Okay, so here's our equilibrium situation. We just plug in the numbers, right? This is going to be squared because they're both the same number in here. And we have Ka is 1.78 times 10 to the minus 4. That was our goal, to calculate the K value for this reaction. So what's the pH of that solution? Well, go back. Here's the hydrogen ion concentration. So we just do the log transformation. And the pH is going to be 1.42. So it's very acidic. In fact, by OSHA standards, that's corrosive. So what would the K value for, the value of Ka for a 4 molar formic acid solution should be what? Is it going to change?
Sorry, I heard something squeaking. I'm not crazy.
I think it's coming from that.
Okay.
I hear the same thing. It's very high pitched.
Yeah.
The K will not change. Right? That's why it's a K. K is constant. So as long as we don't change the temperature, the K is the same. So the value of K for an 8 molar formic acid solution is the same as for a 4 molar formic acid solution. But the percent ionization will change. It's kind of like the difference between equilibrium and equilibrium position. This is an equilibrium position calculation here. So we should have a higher value for a 4 molar than for 8 molar. So if we're looking at this, let me see where I'm going with this one. The discussion won't be wasted. Okay, this is an explanation, I think, for the difference in percent dissociation. So if we're working with a generic acid, there's our Ka for that acid. And if we plug in X value here and X value here and HA minus X for this system, then we say HA is approximately equal to its original. Okay. And the hydrogen ion and the conjugate base are equal to X. Then we get an expression here for the initial conditions. X squared divided by the initial concentration should be equal to K. So what if we add water to HA so that it becomes 1/10 as strong as before? Right? We're going to dilute it, which we're changing the concentration of our acid. So here's what it looks like. The new concentration of A minus is equal to the new concentration of H plus, which is X divided by 10. Right? We've diluted it by a 10 factor of 10. So now our new X value is X divided by 10. And the new value of HA is also the original divided by 10. So which way will the reaction proceed? Le Chatelier, right? If we dilute it, and this originally, if we diluted it, that we decrease the concentration of this one, that one, and that one. Which way will the reaction proceed? We'll calculate the Q. Right? The Q is going to be, this is before equilibrium, so we got this one divided by that one. So we factor out values of 10. Right? This is 10 squared, and that's only 10. So we're still left with a 10 in the denominator here. Right? You see that? Okay. So now we have our Q is 1/10 Ka. So which way? If the Q is less than K, which direction is it going to move? It's going to move this way, right? Because if Q is less than K, that means it doesn't have enough of these. It's got too little of this. Q is small. These are too small. This is too big. So it has to move that direction. That will produce more hydrogen ions in the expression of the dissociation. So now this concentration versus that one in ratio increases. So that's why the percent dissociation is higher for diluted solution. Because it basically shifts the equilibrium that way. All right. The pH of a 4 molar formic acid solution should be compared to the pH of an 8 molar. Remember what I said? The hydrogen ion concentration will actually decrease, but the percent dissociation increases. So we're focusing on the actual concentration. So the pH should be higher, right? It's more basic. Okay. We've diluted it out, in other words. So what is the percent dissociation, percent ionization of a 4 molar formic acid solution? Right? We calculate it. Just do the same thing, ice table. Got our value here, that's the K. Right? And this is the X concentration, and then we take this one and divide by that one times 100. There we go. Oh, excuse me. No, this one. What did I say? Divided by that one? No. This one divided by that one is based upon the original concentration of the acid. 0.67%. So what was it originally? Did it say? 0.67% versus 0.48, was it? I think it was 0.48. 47. 0.47% versus 0.67%. So the percent dissociation has increased. So what's the pH of this solution? 1.57. So it's increased. It was closer to 1.2, I think. Or 1.4. Okay. So how about bases? We'll talk about bases. Bases are actually simpler to deal with. A base is a proton acceptor. And in a basic solution, the pH is going to be greater than 7. If the compound contains hydroxyls, then we can characterize some of them as strong, the same way we do with acids. If they're completely dissociated, that's considered a strong base. All of the alkaline metals, hydroxyls, are strong bases. Lithium, sodium, potassium. But calcium hydroxide is also a strong base. Now, there's a technicality there, because if you look at your solubility chart, calcium hydroxide is insoluble based on that solubility chart. But there are some of these molecules that do go into solution. And when they do, they dissociate completely. So technically, on a chemical basis, calcium hydroxide is a strong base. Okay, calculate the pH of sodium hydroxide solution of this molarity. Well, if we know that it's that concentration of sodium hydroxide, then we know it's going to produce 1 times 10 to the minus third molar hydroxyls. We can do the POH, subtract it from 14, and get the pH. Right? So there's the POH, right? Our negative log transformation. Subtract that from 14, and the pH is 11. So yes, it is basic. It's greater than 7. How about calcium hydroxide? Calcium hydroxide, when it dissociates, if we know that this is the concentration of calcium hydroxide in solution, then when the calcium hydroxide dissociates, it will dissociate both hydroxyls. It'll do them one at a time, but it eventually will release both of them. So now the concentration is twice this for hydroxyls. So that's why we need 2 times 10 to the minus 3 POH, and subtract that from 14 is 11.3. So the same concentration of calcium hydroxide produces a higher pH than sodium hydroxide, simply because it has these extra hydroxyls. Okay. So remember what our definition of a conjugate base is. The acid on one side produces the anion on the other side. That's the conjugate base. So here's the conjugate base reacting with water. And our equilibrium expression will be this Kb, simply because we're starting with this anion reacting with water. And it produces the hydroxide. So this is our equilibrium expression. And the calculations are very similar to acid ice tables. You just have to start with the correct reaction in order to build the ice table. So in this case, we have ammonia, and that should be an arrow. Ammonia reacting with water. The Kb is this value. Okay, so we got ammonia taking a proton from water, making the conjugate acid and the conjugate base. And our expression then, I didn't do the ice table because they're all built the same way. We know this reaction, so we know that this is going to be X and that's going to be X, right? Because there's none to start with. And this is going to subtract the X. And X is going to be very small compared to 2, right? 2 molar solution. So we solve for X. This expression is equal to the Kb. So we solve for X. And we find that the concentration of OH should be 6 times 10 to the minus 3. And the pH, the POH is 2.22 and the pH is 11.78 for this weak base. How do we know it's a weak base? Because of the Kb is very small, which means it's mostly over here. It hadn't reacted with water, so that means it's a weak base, which means this should be a relatively strong acid compared to that. Okay. So remember earlier discussion of conjugate acid, conjugate base. 1 proton at a time leaves the acid and produces a conjugate base as a result. For H3PO4, phosphoric acid, it will dissociate first into 1 proton plus H2PO4 minus. And the K value for this one is 7.5 times 10 to the minus 3. Then we'll take this one, H2PO4 minus, and it will dissociate into 1 proton plus HPO4 2 minus. And its K is equal to 6.2 times 10 to the minus 8. Notice anything about that reaction? The second proton loss is less likely. Right. Minus 3, minus 8. It's 5 orders of magnitude, 100,000 times less likely than this one. Okay, then we can take this one, HPO4 2 minus, and the last proton comes off and gives us PO4 3 minus. With a K value, 5 orders of magnitude lower than that one, 4.8 times 10 to the minus 13. So the moral of this story first is that in multiprotic acids like this one, diprotic, triprotic, whatever the case may be. The first proton comes off the easiest. The second proton is more difficult to remove, and if there's a third proton, it's even more difficult. And it makes sense, because what does this proton have to fight against? A negative charge. You try to pull a positive away from a negative, it's more difficult. And especially if the charge gets bigger, it's more difficult. So that's a sort of a rationalizing of why these values increase. Okay, so the pH of this 1 molar solution, if we remove 1 proton, we also have to think of what's the dominant reaction. The dominant reaction is the first proton, right? Because the second one and the third one are almost negligible. They're not going to come loose in a significant amount that will influence the proton concentration from this one. Okay, so the dominant reaction is the first one, always in a multiprotic dissociation. So that's why we can use this to calculate the hydrogen ion concentration based simply upon the first proton loss. Okay. We made an assumption that gave us a 9.47% error. So what do? Our calculation failed. We're greater than 5%. Well, one thing you can do is go back and do the quadratic. Just leave the x in there and do the calculation as a quadratic. Another way is to do successive approximations. And for this reaction, 1 approximation is probably good enough. So we have an x value here, right? No, here. Hydrogen ion. This x value was determined by the first calculation. If we go back and stick that x value right in here, put that x value in there, and keep these separate. Don't put anything there. Solve for these x's with that new value of x in there. Okay. Then what do you get? Here's what I've done. Put that x in here. Now if we solve for x and test the 5% rule, right? X in this case is 8.2768 times 10 to the minus 2. Then we put that value in our expression here and here, calculate that and compare that to the K value. Now we're less than 1%. That's a successive approximation. And for many calculations in chemistry, successive approximations, not just for acids, but for other reactions, is sometimes the only way to go, especially with equilibrium expressions that have powers of 3, 4, 5, 6, very huge powers in the equilibrium expression. Then successive approximations is the best way to go, because algebraic solutions to those problems, I think there's one for, well, the quadratic, but there's also one for the quadratic. What's the third one? Where you have a power of 3. But my mind's going blank. All I can think of is the fourth one. That's quadratic. Quadratic. Cubic. Quadratic, the cubic equation solution is like that, algebraically. So once you get to 4, 5, and 6 powers, it's just unwieldy. So successive approximations, and now with computers, you can run those approximations easily. All right. So calculating the pH, we just take this value, do our transformation, and we have 1.08 pH. I don't know if that green's going to show up very well on the slide. 1.08 pH, in case you can't see it, for the benefit of our viewing audience. Okay, what's the equilibrium concentration of PO43 minus in this solution? Now, in this case, you do have to work your way through, right? We found out what the pH is. We can calculate what this is. And then we can put those values into another ice table here, and then calculate those values, put those values in here, and we end up with PO43 minus concentration. Okay. So here's the HPO42 minus ice table, right? And as it turns out, what we find is that the X value has not changed. Okay. Let's see. So the X value here, notice that the hydrogen ion concentration, let me back up here. This addition of X here is virtually non-existent. So we can basically ignore it and go with the original, right? This value here is our new X value, but it doesn't change this part of the expression at all. All we have to do is take it into account for this one. Actually for the hydrogen ion concentration. The hydrogen ion concentration here, isn't that the same as we found before at the very beginning? Yeah, that's the original hydrogen ion concentration. Now, let's go back. Here we go. Here it is right there. 8.2768 times 10 to the minus 2. So that value is not significantly impacted by successive deprotonations. So that makes the calculation a lot simpler, because now in order to calculate the not that one. Oops. Here we go. We're looking for this one right here. We know that one. And we know this one from our previous calculations in the ice table. So now we can solve for PO43 minus. And it's very, very small amount. 10 to the minus 19th molar. Okay. So here's our definition that I gave you very early on, and that's an arrow. Should be an arrow.
On ours it is.
It is?
Yeah.
Good.
I meant to tell you that earlier.
Okay. So we react a base and an acid, you always get a salt in water. So what happens if you put a salt into an aqueous solution? Well, if the salt was derived from an acid-base reaction between a strong acid and a strong base, so what would the KCl be derived from? It would be KOH would be the base, and the acid would be hydrochloric acid. These are both strong acid, strong base. That essentially produces KCl plus water. So what happens when you put that in solution? It does not react with water because it doesn't want to. Right? Strong base produces free potassium ions and a hydroxyl, which is a very strong base. Right? It reacts with that hydrogen and makes water. This part right here, right there, it wants to be that exclusively. 10 to the minus 14 in this direction means it wants to be there. So that means these are spectators. right, on both sides, they're spectators. So essentially what you've got is the reaction of water to produce these, right? And that means 10 to the minus 7, 10 to the minus 7, which is a pH of 7. So whenever you react a strong acid with a strong base, you get a neutral solution. That's the moral of this story. Let's see.
Are you doing both slideshows today, or are you doing
Yeah,
14 first and then this, or are you just doing both of these?
I'm gonna do 14 and then we're gonna do 15.
Okay.
Okay. If you can last.
I
We
was
got-
just wondering.
Yeah, we gotta get these out of the way. I paused this. I was looking to see when I was gonna cover. Okay. Let me give you the rules of thumb. The rules of thumb. If you want to know if your solution is going to be acidic or basic or neutral, if the salt that you put in solution is derived from strong acid, strong base reaction, the solution will be neutral. If the salt is derived from a strong base and a weak acid, like that one, potassium acetate, then the solution is going to be basic. So the rule of thumb, it focuses on the origin of that basic. The other way around, if you had and this one, ammonium chloride, weak base derived is from, this one's derived from a weak base, ammonia. This one's derived from a strong acid. This one would be acidic. Okay. Now, what if you get one that's derived from a weak base and a weak acid? For instance, if we have ammonium cyanide, right, from a weak base and a weak acid. You can't tell. Rules of thumb don't work for this one. You have to know something about the dissociation constants, and I mean the equilibrium constants for these in order to tell. So the rule of thumb only works for strong, 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 weak, and weak, strong. The problem with the rule of thumb is it gives you the wrong impression. It gives you the impression that K potassium acetate is basic because of the K, but it's not. It's basic because of the weak acid. Okay, so that's part of the discussion coming up. Here's potassium acetate. These are basic solutions because the conjugate base is strong. So what's the conjugate base? The conjugate base is the anion. Here. So if we look at this situation, C2H3O2, it's like that, there. This is the acid. This is the conjugate base. So if the acid is weak, the conjugate base is strong. So what does that mean? When you put this into solution along with some spectator ion, like potassium, you get a reaction with water. This is a very strong base. It takes that proton and produces hydroxyls plus HC2H2. That's why it's basic, not because of the potassium, because of the strong conjugate base of the weak acid. That's the chemistry. The other was rule of thumb. Okay. Let's see. In this case, for a similar reason, right? This was a weak base, strong conjugate acid. So when you put that in solution, the ammonium gives up its proton very easily. And when it does, it produces lots of hydroniums. That proton, then it acidifies the solution. So on the flip side, this is the reason that the solution is acidic, not that, but this one. Chloride is just a spectator. Okay, so here's your rule of thumb. If the let's see. Actually, that's not a very good explanation. Example, sodium chloride. The solution is neutral, yes, but it's because you have a strong acid, strong base reaction. Well, actually, no, that is a good, okay. No, this is accurate. Because what is sodium and chloride going to do in solution? Nothing. They're spectators, right? There's no reaction produced from sodium ions or chloride ions. So that is accurate. They're neutral cation, neutral anions. In this one, the cation is neutral, but the anion is the conjugate base of a weak acid, which makes it a strong base. It extracts a proton from water and leaves behind hydroxyls. So it's basic. And on the flip side, you have a strong acid derived from a weak base, which makes lots of protons available. And that acidifies the solution. Now, when you get to this one, where you have a weak acid, weak base, then you have to compare the Kas and the Kbs for the two values and see which one wins. And I think, is that the next slide? Yeah, that's the next slide. So if you have a situation where you've got to compare competing reactions, we have a conjugate acid and a conjugate base in competition, you look at the Kas versus the Kbs. If the Ka for the acid is greater than the Kb for the base, then you're going to have an acidic solution, and vice versa. If the Ka and the Kb are equal to one another, then you have a neutral solution. And that happens sometimes. So let's take this example. First of all, calculate the Kb values for these species. Okay. So remember what that is? Kw equals Ka plus Kb. We actually looked at it earlier as pKw equals pH plus pOH. But for these purposes, we're going to remove the K, remove the P. So Kw is equal to Ka times Kb. Remember when we did the long transformation, it put the plus in the middle? Now we're back to the product. So Kw equals Ka times Kb. So in order to calculate the Kb for each one of these, we take the Ka and divide it into Kw. Right? The Kb is equal to Kw divided by Ka. So when we do that, for the acetate ion, the Kb is 5.6 times 10 to the minus 10. And for The cyanide ion, it's a stronger base, 1.5 times 10 to the minus 5. So if you're looking at these anions in solution, then this one at the same concentrations, this one has a stronger attraction for protons, which means the solution is going to be more basic than this one. Okay. So what if we have 1 molar solutions of each one of these guys? Arrange them from lowest to highest pH. There are 2 ways to do this. One is qualitative and one is quantitative. The qualitative approach is look to see first if you've got any strong acids and strong bases. That brackets in both ends. Are there any compounds composed of ions from strong acid, strong base interactions? Okay. Actually, I misspoke. This actually sets the center, the neutral part. So are there any? Let's see. There's sodium chloride. Yep. That will be right dead center, neutral. Okay, so sodium chloride is our neutral. In the middle. Okay? And if we're going from lowest to highest pH, so this is going to be the acidic end, this is going to be the basic end. Okay? Now we look at, are there any strong or moderately strong bases? Put them over here. So let's see, we have a base, yeah, sodium hydroxide. Yeah, that's a strong base. Highest pH. Ammonia will have the next highest pH because these are just pure bases. There's no salt involved. So the strongest would be this one. And then ammonia would be next. Are there any compounds composed of ions from weak acids, strong base interactions? Let's see. There's a strong base, there's a weak acid, sodium cyanide. Right. So that one will be next. The next basic. Are there any acids derived from halogens? That nails down the far end over here, except we can't use HF because it's a weak acid. HBr will be the strongest one here. Let's see, over the edge, bring it back. HBr. Okay. HF is not a strong halogen acid, but it's probably stronger than any of the others. Let's see if there are any other acids in here. No, no pure acid. Well, there's a weak acid right there. So HF will be next. And then HCN will be the next. Now we have to decide the relative position of HCN and ammonium chloride. Okay, HCN is a weak base, is a weak acid, excuse me, higher pH than either HBr or HF. That's true. Ammonium chloride is the salt of a weak base and a strong acid. This fact likely pushes its pH closer to the basic than the HCN, simply because of hold on a second. Closer to the basic than HCN. Very likely HCN is more acidic than it's HCN. Oh, HCN. Here. Yeah, because this is an acid. And ammonium chloride should be here. And then sodium chloride there. So that's the qualitative approach. And there's the order. HF, HCN, ammonium chloride, sodium chloride. Okay. Now the other approach is quantitative. Examine the Kas and the Kbs for these values. We use, here's our neutral position right here. This orders the acidic ones. The Ka for this expression is 10 to the minus 10th, 6,2, 10 to the minus 10th, 10 to the minus 4. And that's a strong acid. This is a strong base. Then the Kbs on the, we know these are going to be the basic side. So then we look at the Kbs to order these. Right, the more basic is the higher number. So ammonia is more basic than sodium cyanide. That's how we get this one relative to that one. Wait a minute, ammonia is not in there. Yeah, it is. There's ammonia. How did I leave ammonia? Oh, there's ammonia. Okay, it's more basic. Okay, those are good. Those are good. But we order them based upon the K values, depending on whether it's on the basic side or the acidic side. So you do have to figure out which side of neutral is it going to be on. And that gives us the same answer. Let's see. We should be coming down to the end of this chapter, pretty close. All right. Now we're going to actually calculate the pH. So we have this solution of sodium fluoride, 0.3 molar solution of sodium fluoride. What happens to sodium fluoride when you put it in the solution? It completely breaks apart. Sodium ions and fluoride ions. All right. So what are the major species? Here we go. Sodium ions, fluoride ions, and water. Those are the major species. These are the reaction. This is the acidic reaction of HF that corresponds to this value. And then here's the Ka for that reaction. What are the possibilities for reactions? We're going to go from sublime to ridiculous here. Fluoride ions are going to react with water, produce HF and OH minus. Okay. Water reacts with itself. That's a given. How about sodium? Does sodium react with water? No. Sodium's a spectator. It doesn't want any hydroxyls. It prefers just to be like it is. Sodium react with fluoride? No, it goes into solution. Right? So 3 and 4, you don't even have to consider those. So what we have is, we've got this reaction competing with this reaction. The water reaction competing with the fluoride in water. All right, so let's look at the value here. What's the Kb? This has to be expressed in terms of Kb because we've got fluoride ions in water, not HF dissociating. So we need the Kb. There it is, 1.3 times 10 to the minus 11. We do this calculation. And then water, of course, is 10 to the minus 14. So the Kb for the first reaction is over 1,000 times larger than Kw. That means this is the dominant reaction right here. This is a much larger value than the K for that value. Oh, is that all we had to do with it? Calculate the pH of a 0.7 molar aqueous solution of sodium cyanide. Okay, so we're gonna do the same thing again. What are the major species? Sodium, cyanide, iron, water. Throw out these because they make no sense whatsoever. Compare the first two. Right? So this is the KB for the first one. Excuse me. Yeah, the KB for the first reaction is this one. And notice that the KB here is much, much larger than the KW. So that's the dominant reaction. This one right here. We start off with this one, and we virtually have none of these. So there's our ice table. Here's our solution, and we're going to say that X is too small to matter. And that means X is 3.46 times 10 to the minus 3, which means the POH, remember X here is OH. So the POH is 2.46. That means the pH is 11.54. Okay, and we didn't do it on the board, but if you run the 5% rule, you'll find that it's well within it's less than 5% difference. Okay, so let's look at models that control the acidity in these binary compounds, these acids and bases. Bond polarity is one thing that's involved, right? What's the polarity of the bond? If the bond is very polar, that means that the hydrogen ion, or the hydroxyl for that matter, is more free to leave. Right? The electron density is already being pulled significantly toward one side, and the other part can leave easily. Then there's the bond strength. Right? When we're talking about the strength of an acid or the strength of a base, let's focus on acids for now. The bond strength, low is good. If the bond strength is low, that means the proton can leave. Or if the bond polarity is high, that also means the proton can leave. It's not being held very strongly. So if we looked at this homologous series, the acids formed from all the halogens, we find that the bond strength decreases as we go down in that group. So that would imply that this would be stronger than this one, which is stronger than that one, which is stronger than this one. In fact, the bond strength is so high here that this one is classified as a weak acid. But the rest of the halogens form strong acids. Okay, other types of acids. The ones that have oxygen in them. So these are going to be the polyatomics. Right? The ones with, say, chlorate ion, the perchlorate ion, chlorite ion, and the hypochlorite. We form acids with those. What would be the trend? When we're looking at the strength of these acids, what makes a difference? The more oxygens you have, the stronger the acid. Okay, let me say that again. The more oxygens you have in a series, the stronger the acid. It's logical, right? We've already said that the polarity of the bond with the hydrogen means that the more polar that bond, the stronger the acid. So what do we have here? Well, we have a chlorine and an oxygen and a hydrogen. Here we have a chlorine and an oxygen and an oxygen and a hydrogen. Here we have a chlorine and an oxygen and an oxygen and an oxygen and hydrogen. And here we have a chlorine, oxygen, 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 hydrogen. So what do we know about oxygen relative to these others? Well, the halogens are very electronegative, but the oxygen is also electronegative. And when you get the bond polarity here, well, actually chlorine would be higher. But what you're doing is electron density is being transferred away from the chlorine, which draws even more electron density away from this bond. So each of these hydrogens is polar, but which one is the most polar bond? The most polar is the one that has more oxygens drawing electron density away from. So that explains why the more oxygens, the stronger the acid, because it creates a more and more polar bond with the hydrogen. Okay? Okay, and we can verify this with K values. So here's the hypochlorous acid with the 10 to the minus 8, the chlorous acid 10 to the minus 2, the chloric acid is about 1, so we're getting into the strong range here. And then the perchloric acid is 10 to the 7th K value, which means it is completely dissociated. It is a very strong acid. Okay, what else can we say? Electron negativities. So if we want to compare apples. So if we have an oxygen bound to some other element, and the hydrogen over here, this is the acidic hydrogen. Then as we go down, we decrease the electron negativity. So between these here, as we're going down in the halogen group, we decrease the electron negativity of the halogen, and we weaken the acid. Right? We can see minus 11, minus 9, minus 8. So the stronger, these all have one oxygen in them. Right? So that's not the focus. The focus here is electronegativity. Right? So this is less electronegative, which means this is the weaker acid. This is a little bit stronger, and this is even stronger still. And then if we put a methyl group in here, like that, we find that its electronegativity as a group is 2.3. It's even weaker. So which one is this? You recognize that compound? Methanol. That's methanol. You didn't think of methanol as an acid, did you? Methanol is an alcohol, right? Wood alcohol is the one that'll make you go blind if you drink it. But you can think of ethanol as an acid also, right? The drinkable kind. It has a dissociation constant for this one, but it's even weaker for other reasons. No, we're not going to go into those today. How come we left off the fluorine in here? Because HOF, when you can make it, when you put it in aqueous solution, it completely dissociates, just decomposes in water to make HF and hydrogen peroxide. So then you're not really measuring the acidity of this group, you're measuring the acidity of that one and that one combined. Okay, other types of compound that produce acidic or basic solutions. Right. The first one we want to look at is the acidic oxides. And those are acid anhydrides. This is another name for them. They are always composed of a non-metal oxide. So sulfur dioxide, nitrogen dioxide, carbon dioxide, those are all acidic oxides. When you put them in solution, they produce acidic solutions. And here's how they do it. When you put that gas in solution with water, the reaction is such that it combines with the water to produce this acid. Right? That's sulfurous acid. So sulfur dioxide and water makes sulfurous acid. That's the acidic solution. Same thing will happen with these. CO2 is a good one, right? When you carbonate water with make pot, you get CO2 combined with water, and it produces H2CO3 in aqueous solution. That's carbonic acid. Right? Carbonate, polyatomic ion, A's become X, carbonic acid. Right? They all do that, and that's non-metal oxides. All do that, make acidic solutions. Then the other kind, the basic anhydrides, a metal oxide. So what happens when the metal oxide goes into solution? K2O and CaO, when they go into solution, they also react with water. But they react with water in such a way that we produce bases. KOH, this would produce calcium hydroxide. You can do it with sodium oxide, or magnesium oxide, and they would make these hydroxides when they react with water. So the metal oxides produce basic solutions. And the best ones are way on the left-hand side. When you get into the middle of the table, transition metals, and they're a little squirrelier. Simply because they don't go into solution as well. Like if you try to do this with iron 3 hydroxide or iron 3 oxide, you get nothing. Because it doesn't go into solution, that's rust. Okay, now I mentioned earlier that there were several theories for acid bases. We talked about Arrhenius first, and historically speaking, then came Bronsted Lowry. And now we come to Lewis acids and bases. G.N. Lewis was a famous chemist who gave us the Lewis dot structures. He also worked with acids and bases in non-aqueous environments. Now, this works for aqueous as well as non-aqueous, but it was necessitated predominantly because there were reactions, particularly organic reactions, that were being carried out in non-aqueous solutions, and we needed an explanation for the reactions that were occurring. So instead of falling back on water reactions, we had to come up with a different definition for acids and bases. And Lewis provided that definition, and it blends in with the previous definitions. In other words, it expands the universe for acid base from Arrhenius to Bronsted Lowry to Lewis, covers the universe. So a Lewis acid, according to Lewis, well, obviously, a Lewis acid is an electron pair acceptor. An electron pair acceptor is a Lewis acid. So if we look at that in terms of Bronsted Lowry, what do we got? We got HCl, right? 2 electrons here. Okay. If it reacts with water, what do we normally get? We get H3O plus Cl minus. So the electron pair acceptor is here. That chloride accepts those electron pairs and produces this positive proton and chloride. So anytime the electron pair is transferred, is accepted, you have an acid, and anytime it's donated, you have a base. Here's an example. Now, in this case, it's not obvious from the Bronsted-Lowry model that we're not actually transferring a proton, are we? Not in this model. What we've got is an aluminum 3+ ion plus 6 waters. when we have the aluminum combined with these 6 waters, we have the Lewis acid, which is the electron pair acceptor. This is the acceptor. It accepts the electron pairs from water molecules. And when it does that, it forms this bond. So here's the Lewis acid, there's the Lewis base, which is the electron pair donor. It's kind of the flip side. In the Lewis universe, the donor is the base. Only it's not donating a proton, it's donating an electron pair. Okay. So there they all put together. Summary. Right, when you're doing an acid-base equilibrium problem, what's the major species, and then what's the chemical reaction that is dominant? Then move from there. And when we get to the next chapter, we're going to look at reactions in which we might need to consider both possibilities. In other words, let the reaction go to completion, then treat it as an equilibrium and come backwards. If you try to go equilibrium from the front side, it's almost impossible to do.
Okay, so now we're going to do 15.
And let's see, what do we call this one?
Acid-base.
Acid-base equilibrium.
Yeah.
I thought that's what we were talking about already.
No.
Okay, in this context, acid-base equilibrium is
Buffers. That's where we're headed. So let me call that one up. Here. All right. So we'll just, since we're already moving at 60 miles an hour, we'll just keep adding steam and move right into chapter 15. First concept we need to bring up is the common ion effect. When we're talking about an equilibrium, we can shift the equilibrium only if there is a common ion involved in the reaction. We sort of touched on this, but not relative to ions, but when we were talking about Le Chatelier's principle, and what if you add an inert gas? You're increasing the pressure, yeah, but there's no effect on the equilibrium because the inert gas isn't part of the equilibrium, right? It's a spectator, so to speak. But if we were to add a gas of one of the components, either the reactants or products, then we would shift the equilibrium. Similar to that is shifting equilibrium with ions. If you add an ion or you subtract an ion from a reaction, if it's common to that reaction, it will affect its equilibrium. That's the common ion effect. So, an example where we have hydrocyanic acid reacting with water produces hydronium ions and the cyanide conjugate base. What if we add sodium cyanide to this reaction? Is there a common ion? Right, sodium cyanide. Well, sodium is not a common ion, so it will have no effect. But the cyanide is a common ion. And then we'll enter this reaction here and shift the equilibrium back to the left. Right? So if we add a cyanide ion to this reaction, it will shift the reaction this way, consuming protons, or hydroniums, which means what? It will make the solution more basic because we're consuming hydrogen ions. Or less acidic, let's say. Okay, we're still headed toward buffers. These concepts are essential for understanding buffers. What happens, because a buffer is an equilibrium situation, and it's an equilibrium situation that uses Le Chatelier's principle to determine where it's going to be in the equilibrium. Okay. In chemical terms, a buffer solution is one which changes very little, only slight changes in pH if you add an acid or a base to an equilibrium mixture solution. Right? It resists a change in pH. It does not have a constant pH, but the pH change is very small. Okay, that's what we mean by buffer. Now, in the greater world of chemistry and in fact, non-chemistry, buffer has a broader meaning. In other words, but it always resists a change. A buffer resists a change of any kind. And in this context, it resists a change in pH. Okay. So in these cases, if you have an original buffered solution, in order to get to the new pH, we do stoichiometry calculations. Assume that when you add the acid, the hydrogen ions, or the hydroxyls, all of them are reacted. They're completely reacted to one side. That's your stoichiometry. Then you take that new position and apply equilibrium. So that's when the ice table comes in. Okay. Let's see. How does a buffer work? Actually, this is not a good explanation. Let's look at it this way. Most buffer solutions are composed of a weak acid and its conjugate base. So what is that reaction in reality? The acid, a weak acid plus water produces hydronium ions plus conjugate base. Okay? In a buffered solution, we don't start out with this one necessarily, but we start out with amounts of both of them. So we have a certain amount of this and a certain amount of that in solution at the same time. We set it up that way so that the equilibrium has some of this and some of that in it. Okay. Now the equilibrium is established. What happens if you add acid to this solution? Right? If you add acid to this solution, right, which way is the reaction going to go? Go that way. Right? Le Chatelier says you disturb the equilibrium by adding acid, so it's going to go back that way. What does that do? That consumes some of the added acid. So if you consume a large part of that added acid, if this is a weak base, a weak acid, that means this is a strong conjugate base. Now, if you add acid to that, this strong conjugate base is going to suck up those protons quick. It's going to have a strong attraction to those extra protons, which means it uses up most of these, not all of them, but most of them. So what happens to the concentration here? It's almost constant. So that's how the buffer solution takes care of adding acid to it. How does it take care of adding base? Well, that's over here. Okay. Same situation. Where does the base enter in? Let's say our base is OH minus. So if we add base, say it's sodium hydroxide. Right? Sodium's a spectator. The hydroxide, where does it react? Well, it's looking for protons, right? It's looking for protons. It's looking for protons. So what does that produce? That plus that produces water. Let's see. Yeah, it's more likely to react with this one because this is a very, very strong base.
So it's going to pick up some of those. But what happens when it removes some of these? Right? We remove some of those with this reaction. Which way is the reaction going to go? That way. Le Chatelier says, you remove product, the reaction shifts to replace. Okay, so that will give us the stability in the pH for the base. Did somebody come in? No? Nobody else? Okay. Let's see. Now, expressions of for a weak acid, this is HA yields H plus and A minus. So now we're going to go to the simplified version, where we have HA and A minus and then H plus. That's the simplified version. So the Ka for this acid is expressed as hydrogen ions, conjugate base over the weak acid. Okay? Now, suppose we want to know the pH of this solution. How would we solve that? Well, you have to solve it for the hydrogen ions first, don't you? Right? If you want to know the pH of this solution, we got to know what the hydrogen ions are. So if we solve it for hydrogen ion concentration, that means that Ka times HA, and then this one is denominator, numerator, this was numerator, denominator, is over A minus. Okay, that's where that one comes from. And it was first proposed by Henderson. He published his work in 1908 and produced this equation. He said, if I want to know the pH, I need these three factors. I need to know the Ka for the weak acid. I need to know the HA and the A minus at equilibrium. Okay. Then along came Sorensen's. Well, actually, Henderson proposed this before he knew anything about pH. Right, 1908. Then Sorensen came along and said, all right, but I like pH better. So then Hasselbalch followed up and said, okay, let's apply the log transformation of Sorensen to Henderson's equation. That's why it's called the Henderson-Hasselbalch equation. So if we apply the negative log to this expression, just do the whole thing. Negative log of that whole expression, what do you get? Well, you get the negative log of the hydrogen ion concentration. That's obvious. Then we get the negative log of Ka, and times means we plus, which means negative. Negative log of this ratio. Now, why don't we just split that out? Say, right, the log of this expression would be the log of that minus the log of this. The reason we kept them together was because ultimately we're only interested in the ratio of this one to this one. The concentration is irrelevant. Well, it's not irrelevant, but it's another discussion. But if we express it this way, then what do you have? Well, the negative log of that is pH, correct? The negative log of this is pKa. And then we just leave this one alone. Negative log of that ratio. Okay? But we don't like negatives. Right? We want to get rid of that negative. So how do you get rid of a negative in the log expression? Well, this log, if we change that to positive, then it just flips that expression. So now if we say positive log, we got the denominator on top, the original denominator on top, and the numerator is now on the bottom. Okay, so that is the Henderson-Hasselbalch equation, derived. I think I did it here. Yeah. So we take negative log of the whole thing through, then we change the sign. That's the final equation. We don't bother taking the negative logs of these, just say PA minus and PHA. That's not as useful. So Hasselbalch said, let's just leave this ratio together, because if we know this ratio, then we can compare it to the pK value. We can add it to or subtract it away from, depending on the calculation. And this is going to be in calculated form anyway. It's not going to be in a P form. The concentration of A minus and the concentration of HA are going to be different for every solution. So we'll just leave that one alone. And that's the Henderson-Hasselbalch equation. So what does that mean? That means that it doesn't matter what the concentration of these two are. It only matters what's their ratio. Okay. So you're going to be glad that the Henderson-Hasselbalch equation is available, because it simplifies calculations eventually. So if we know this situation, we can calculate the pH of this buffer solution, and we know it's 0.45 molar acetic acid and 0.85 molar sodium acetate. Okay. So when we put those two solutions together, we have established those concentrations on either side of the equation. We plug those values in here and solve the equation with its Ka, right? There's the Ka for acetic acid, and that's what the Ka means. It's the Ka of the weak acid in this mixture. So acetic acid is the one we use right here. We don't need the Kb for acetate. We only need the Ka for acetic acid and the concentrations of the acid in the conjugate base. And the pH is 5.02. Okay. Let's see. Okay, that's nothing new. What we do need is, as a practical matter for buffers, in order to have an effective buffer, you need large amounts of these two. Because according to that first equation where I showed you how acids added and bases added were consumed by the equation, by the reaction, if you exceed the amount of available reactants when you add acid or base, then all bets are off. It could go acid or base, just like that. That's known as buffer capacity. So you need large enough concentrations here of the conjugate base and the acid, so that if you add acid or base, there will be sufficient concentration to react with them. Okay, so from a chemist standpoint, you can make these huge amounts, 1 molar each. But if you're using buffers, as is often the case in biological systems, you have to be careful, because you can only go up to such a concentration before you start to affect the enzyme systems and the reactions of your biochemical reaction matrix. Some effects of high concentrations of these in biological systems is they can denature the enzyme if the ionic concentration is high enough. Or you could cause an osmotic shift for the cell. In other words, if this is very high on the outside of the cell, it'll suck water out of the cell and crenate it, crenulate it. Okay. So, and there are recipes for all kinds of buffers for natural systems that take that fact into account. Some of them are combination buffers. Right? We're not going to get into those. We're just doing single reaction buffers. And what those combination buffers do is, if it's buffered in this region, then it's fairly stable. And if it exceeds that, it's buffered at a different pH. Okay, that's the buffering capacity. The amount of protons or hydroxide ions the buffer can absorb without a significant change in pH. So let's see, do we have a calculation for that? Buffering capacity is quantified in the following equation. Okay, so this beta stands for buffering capacity, and this delta N and delta pH. So this is the change in pH and the change in N, whatever that stands for. Here it is. Change in normality of the acid or base. So if you add an acid, you can calculate how much change in normality that will be without the buffer. And then this is the response. So when you change the normality of the acid or base by a certain amount, then you want to see a very small change in pH. And the smaller this with the larger that means a bigger beta. So the larger the beta, the better. Okay. For a monoprotic acid, the normality equals the molarity. Right. We studied normality when we talked about solutions. We did, didn't we? That was first semester. We talked about solutions. Yeah. Okay. The normality for a diprotic, like sulfuric acid, one normal only requires half molarity. So a 0.5 molar sulfuric acid is actually one normal because it produces 2 protons each. So you only need half as much to give you the same normality as, say, HCl. Okay, what's a titration curve? That's the one we're going to do with our lab. A titration curve in acid-base chemistry and we're going to say, for our purposes here, we're starting off with an acid, a known amount of acid, and we're going to add base to it, little at a time. So this is added base. And this is the pH. Okay? So as you add base, you start off at a low pH for your acid, right? Somewhere down here maybe. And it immediately goes up as we add base. But then it flattens out really quick, like that. It only has a very slight positive slope. This is the buffer zone right here. As we add base to that acid, the pH doesn't change very much. But when we get to the point where we've used up all our buffer capacity, then the pH changes rapidly, like that. And then we eventually reach a place where adding more base doesn't make a whole lot of difference. So that's your typical acid-base titration curve, where you start with acid and you add a little base incrementally. So the equivalence point, or the stoichiometric point for this acid-base reaction, is the one where acid plus base yields the salt plus water. When you reach the stoichiometric point, where the base is equal to the acid, you're right here. So that volume of base relative to the volume of acid means that the acid base are equal. This is the equivalence point. Okay. Now, titrations can be done for almost any kind of reaction. It doesn't have to be acid-base. This is an acid-base titration. You can do titrations with almost anything else. What you're aiming for in a titration is the equivalence point, where you've reached the stoichiometric equivalence. You want to find out what that position is. In an acid-base reaction, you want to know what the pH is. Right here. What's the pH at equivalence? And here's an example, right? We start off with nitric acid and sodium hydroxide. This is not very well buffered, right? That slope is pretty steep. So you're not going to get a good buffer situation here with nitric and sodium hydroxide. But that is a titration where you find the equivalence point. And the equivalence point where they're actually equal is 7. Remember when we add a strong acid and a strong base, a salt made from those two, we get equivalence. That's why we get neutral pH. That's why the equivalence point is neutral. If you go the other direction, right, if you add acid to the base, you start high and go low, but the equivalence point is the same. Okay, when we're doing a titration, you've got two problems. One is the stoichiometry for the titration, right? Equivalence point. That's the first step. You determine at what point do we have equivalence? What amount of added base to that amount of acid do we have equivalence? And that's the pH. And then once you reach this point, you stop the titration and you let the solution equilibrate. And that's the second part of the problem, the equilibrium problem. When you have a weak acid equilibrium, this is where you calculate the pH. For the strong acid, strong base, you know what it's going to be. It's going to be 7 every time. So if we have this weak acid, hydrocyanic acid, we're titrating it with sodium hydroxide. Start off with 0.1 mole of HCN in 1 liter, and we're adding 0.04 mole of sodium hydroxide in 1 liter. So we're already given the equivalence situation. The major species are, we now have HCN, sodium ions, hydroxide ions, and water. We don't have a major amount of hydrogen ions or cyanide ions in this case. Okay, so here are our possibilities. These two get thrown out. Actually, the 3 of them. We throw these 2 out. They're just stupid. But can we react HCN with OH? Yeah, you can do that. And it'll strip a hydrogen off of that, make CN minus and H2O, because this is a very strong base. It takes the hydrogen ion off of there, makes that. Okay, so these are our possibilities. Which reaction controls the pH? Well, the stoichiometry of the reaction is this one, where we've added base to the weak acid. And we make this situation. Now that we've got this one after the stoichiometry, then we have a different situation. So we're doing this one first. What are the major species after this reaction? After that reaction, now we have the major species HCN, CN minus, H2O, and sodium. Right? So we do have some of this because this has stripped away some hydrogen and left us with that one. Let's see. Oh, I hate it when it does that. We get wound up, ready to do a calculation, and it just says, we're done. Okay, so now we're gonna titrate acetic acid and sodium hydroxide, which is actually what we're going to do next week. So 0.2 moles of this with 0.03 moles of sodium hydroxide in 1 liter of aqueous solution. What's the pH? That's the question. Okay, major species. Sodium hydroxide ions, acetic acid, and water. Okay. So those are possible reactions, and throw these out. So we have this one combined with that produces this. Right? So which reaction controls the pH? Well, it looks like okay. This is a Ka and this is a Kb. So we have to look at it in terms of what reaction is taking place. We can't compare these directly yet. Why? Because with this one, we need some of that. Right? And we're just now producing that. So we're going to produce it first. Then we can invoke a different reaction. So the Kb for this reaction is actually Kb should be that one with water. Yeah. Strong base reacts with this proton donor. So now the major species are hydroxyls here. Some more of that. And what about this one? Major species, right? We don't have any of this one yet because we're just now starting. And we don't have any of that in the equation. Why? Because it's pure water. It doesn't count. Its concentration doesn't change significantly. So we only have to be concerned with these. All right. So if we start off with initially with this one, 0.2 molar. So how do we get 0.2 molar? Back up. Here we go. 0.2 mole in 1 liter. And then 0.03 mole in 1 liter. All right. So now we know our concentrations. 0.2 molar and 0.03 molar. It's where we start. So if we use all of this up, this is the stoichiometry part of the problem. If we use all of that up, now we've got no hydroxyls left. And we've got all of these, and then a little bit of this left. So now that's our starting point for equilibrium. But the equilibrium is going to be this one reacted with water to produce that one. So now we've got some acid. Right? We're reestablishing equilibrium. So this acid and that water produced maybe some more of this. Is that really the way it's going? Well, let's look. Let's go back. Any hydrogen ions here? None to speak of, because that's a weak acid. Right? So what we're doing is we're saying the reaction has to go to the right. Because we've consumed all of the hydrogen ions with hydroxyls, right? So it has to go to the right. That's why we use this reaction. So our starting position now is 0.17 here and 0.03 there. And our reestablish equilibrium. We get rid of this X, right? That one times that one divided by this one equals that. So the pH is 3.99. Okay? What if we use Henderson-Hasselbalch? Well, Henderson-Hasselbalch says that our A minus is here, and our HA is here, and our pKa for the reaction is 4.74. So you have to take the Ka for acetic acid and convert it to pKa. Right? What was it? 10 to the minus fourth. 1.8 times 10 to the minus fourth. Fifth. You convert it to 4.74 pKa. Then you can take this ratio and that, and it gives you the same pH. without having to go through all the other calculations. (1.8 times 10 to the minus 5, there it is. Now, the purpose of the next week's lab is to determine that experimentally. And we'll do it from a titration curve. Okay. Let me take a quick look here at 15 and see if that discussion is coming. I don't want to steal my own thunder. Okay. Let me talk about it now. So when we're talking about pKa, we've got here a weak acid plus water yields hydronium plus conjugate base. Now we're going to substitute, we're going to get rid of this one and just call this one H plus. So when we write the Henderson-Hasselbalch equation for this reaction, we find that pH is equal to pKa for the acid plus the log of the conjugate base over the weak acid. So notice when we add base to this point, what does that mean? That means we've consumed all of that. There's none left. The HA is gone by that previous expression, the base and the acid added together. So at this point, there's no HA. We know how much HA was originally down here, right? Well, that's not equilibrium. But our starting concentration of HA here was a certain amount. Now it's 0. So if this is the equivalence point where we've used up all of this, now it's all there. So this is 0 and that's infinity. But what's going on in here? Where would you like to be if you want to change the pH? Very little. Add base or add acid to bring it backwards. Where would be the best place to be? Right in the middle, right? Halfway. Halfway is your best buffer place to be, which means 1/2 equivalence. 1/2 equivalence is the best buffer position. So what's happening right here? Well, if all the HA is used up here, where's half of it used up? Right there. So if HA is equal to 1/2 of the original HA, what's the A minus? Well, if only half of this is left, where did it go? Over here. So the concentration of A minus and HA are equal at this point, right? That's equal to A minus. So at this point, HA and A minus are equal. So what's this one divided by that one? It's equal to 1, isn't it? If these are equal, that's equal to 1. So log of 1 is 0. So at this point, that term goes out. And at this point, pH is equal to pKa. Okay? So all we have to do is titrate it, find the midpoint. What's the pH? That's equal to pKa. And do the anti-log of the negative pKa, and we can find the Ka. And it should be close to that value. So that's the whole lab next week. Doing this and then calculating the Ka from that. I think there's a discussion in the method too about all that stuff if you want to read it. Okay, so now that we have, let's see, pH of 100 milliliter solution of 0.1 molar acetic acid, which has a Ka value of 1 times 10 to the minus 5. So 0.1 molar here. We're going to lose some of it there. And that produces 0.1 minus X. And here's our ice expression for the Ka. We're going to say X is very small. And our calculation gives us a pH of 2.87. All right, so that's where we start. So if this were Ka, this starting position right here for that concentration of solution would be 2.87. And then we add a little base and it would jump up here into this region and then it would stop changing significantly. Am I running out of time?
No.
1250, okay. So now what if we calculate the pH of a solution made by mixing 100 milliliters of a 0.1 molar solution of acetic acid which has a Ka of this value, and 50 milliliters of 0.1 molar sodium hydroxide solution. We're going to let the reaction go to completion first, which means we're at the equivalence point. Well, actually, no, we're not at the equivalence point. Because we haven't added the same amount of acid, right? In 100 milliliter solution, 0.1 molar, 50 milliliters, 0.1 sodium hydroxide. If it were equivalence, that would be 100 milliliters of the same concentration. But we're not at equivalence. We're somewhere in between. So what we're going to do is let the reaction go to completion. So we're going to add this with the base. Right? This is the molarity after we add them together. Molarity is 0.1 to begin with. But after we add 50 milliliters, it's 0.1 is diluted to 150 milliliters. So we can do that calculation by our M1B1 equals M2B2. Right? The initial concentration is 0.1 molar. And what's its volume? 100 milliliters. We don't know this one, but we do know the final volume, which is 150 milliliters. Right? So divide 150 into this one, and M2 becomes 0.0667. That's where that came from. Right there. And do the same thing for this one. And this is our starting point. We're going to let the reaction go to completion. 0.0333 molar is used up here, right? Because they're 1-to-1, we didn't use up all the acetic acid. So this is what's left over, acetic acid, and this is what's produced as acetate ion. Oops. Now, oh, that's the same reaction as before. 0.034, 0.034. That's wrong, isn't it? What is it on your
0.034.
right? Because if we subtract that from this one, that's 3.44. 0.034. Right, it should be the same as this. Okay, so that's a mistake. Mark it. Where is it? Here it is. Okay. I think the calculation is still right. Yeah. Okay, so here it's correct. Right there. And those are the equilibrium concentrations of these two, the conjugate base and the acid. So the conjugate base goes on top, the acid goes on the bottom, plug in those values. And our Henderson-Hasselbalch said the pH is 4.73. Okay. So by adding that amount of base, we've produced a buffer that's very close to the middle of the buffer region, 4.74 or 4.73. How about this one? Up to this point, we've been talking about weak acids and their conjugate bases. What if we make a buffer out of a weak base and its conjugate acid? So we got 100 milliliters of 0.1 molar solution of ammonia with a Kb of this value, and we add 50 milliliters of this ammonium, 0.1 mole ammonium chloride solution. So what does that look like? Well, we've got ammonia reacting with water to produce ammonium and hydroxide, right? That reaction goes to completion. So we're starting off with this much ammonia and this much ammonium concentration. And we calculate the concentration like we did before, diluting it from 100 to 150 milliliters or from 50 to 150 milliliters. And we calculate the final concentration, the new concentration before the stoichiometry. So we've got this one to start with, this one to start with, none of that. And this is our actually, that's not equilibrium. We're letting that reaction go to completion, aren't we? There we go. So our Kb expression is that one times that one divided by this one. That one times that one divided by this one. Okay. And we solve for X, and X is what? X is the hydroxyl ion concentration. And then we can calculate the pH. In this case, we didn't need to go to completion. Right, we didn't need to go to completion. We could use the equilibrium immediately. Because this is the base, and this is the conjugate acid. And we know what the concentrations are to start with. Okay, so that's the long way to calculate. Let's see, are we going to do the Henderson-Hasselbalch? Yeah, here we go. So this is the approximate equilibrium position that we calculated earlier. Right? .00667, 0.033. There it is. Approximate equilibrium position. We plug it in the formula, right? And we end up with 9.56, which should be 9.56. There we go. Okay, so you can do it either way. All right. So what would be the pH of a solution if we combined 1 liter of 0.5 molar ammonia and 0.5 liters of 0.1 molar ammonium chloride? First of all, do we have a common ion here? Well, yeah, ammonia, if it reacts with water, is going to produce ammonium plus hydroxyls. So if we add some more of this to it, that's going to shift the reaction. So we've got this one, we've got this solution first, ammonia and ammonium chloride, and then we're going to add a 1/10 mole of HCl as a gas. Now, why are we doing it as a gas? That's so that we don't change the volume. We're going to bubble that gas into it. So our initial amount of ammonia is 0.5 mole, and initial amount of ammonium added extra is 0.1 mole. Right, we just calculate M times V. Okay, so this is before the reaction. We have this much, and we also have added this much hydrogen ions as HCl. Okay. We're going to let this go to completion. So we have none of this left, and we have this one, that one, in our new amounts. Right? This is not concentration, so it's not an ice table. It's just a sort of a budget of total amounts. And then we're going to use those to calculate concentration. Right? So now our new volume is 1.5 liters, and there's our new concentration of base and the acid. Now that we know that value, we can plug that into our equation. There's our pKa calculation. Right? We were given what? pKb. Right? That's odd. That's almost the same numerical value as the pKa of acetic acid. So what that tells me is if you have ammonium acetate, put it in solution, it's going to be neutral. Because the pKa of this acetate and the pKb of the ammonia are almost equal, which means nobody wins. Okay, so now that we have these values here, and we know the pKa, we can calculate the pH is 9.55. Now let's see, is this a different problem? pH of the solution at the equivalence point. Ah, okay. So now what's the pH at the equivalence point? This is a good exercise. And the reason being that when we do repetitive titrations to determine the concentration of acid in solution by matching it with the base, that's what equivalence titration will do for us. We did that in the first semester, where we had we were standardizing a base against acetic acid, and then we took the standardized base and we titrated against citric acid. We wanted to know the equivalence of citric acid, how many moles of citric acid were there. We were going to the equivalence point. But the same thing happens with, if you have to do a lot of those titrations, you want to use a system that is quick, and a pH meter is not quick. So we use an acid-base indicator. And we need to know what is the pH at equivalence. We had to answer that question. If we know the pH at equivalence for our reaction, then we can pick a buffer, an indicator that will change colors very near that value. That's what we're looking for. So in this case, we've got acetic acid and sodium hydroxide in these amounts, these quantities. So here's the total volume, right? We need to know the total volume. And so before the reaction, the concentration is equal to 0.01 per 0.2 liters. So 0.01 is 0.1 times 100. Then divided by 2. We're doing that M1V1 equals M2V2, actually, is what's happening here. So this is the new concentration at the beginning of the reaction for acetic acid. And then the concentration of base is 0.1 molar. Oh, it's at the equivalence point. So the equivalence point says we don't need to calculate the concentration. The equivalence point says that the hydroxyls equals the hydrogen ions. So that's why the concentration of hydroxyl has to be equal to this. It's gone, it's gone. Now we've got 0 of this, 0 of that, and it's all here. Acetate ion. Now the dominant reaction is acetate ion plus water. Okay, we've gone to completion. Now the acetate ion is going to react with water and produce this expression. So we need to know the Kb for the acetate, and that's this one. Right? This is for the acetic acid, and the Kb we divided into the Kw. That's the Kb for this reaction. Right? So when we take that expression, right, this times that divided by that is equal to the Kb, and we're going to say that that X is too small to deal with. So now we just do our calculation and find that the X, or the OH, is this concentration, the POH is that, and the pH is this. So at 8.72, you should see equivalence. So when we, well, I erased it. When we do the titration, that steep part should be very close to 8.72 in the middle of that steep climb, right there. Well, there it is. Very close to 9. Not exactly, but close. And you'll notice that for different concentrations, depending on the pKa of the acid, the weak acid, the titration curve will look different. So for strong acids, it's like this. They just virtually flat all the way over until you hit the equivalence point. And then as you increase the Ka, you get this part of the curve, the buffer part of the curve shifts upwards. So if you want to buffer at a higher pH, you need a weaker acid. So hydrocyanic acid would buffer in this region, whereas acetic acid would buffer in this region. If we titrate ammonia, it's going to go the other direction because ammonia starts off at a high pH. And then we add acid to bring it down. So this is the middle of the buffer zone for ammonia right here. And it's always going to be half the volume at the equivalence point. So if it's 50, 25 will be right in the middle of the buffer zone for that type of titration. Okay, the equivalence point is a stoichiometric value, and we determine it by titration and determine the pH at the equivalence point. That is, the equivalence point is on that titration curve. If we want to use a color indicator, we have to give it a different name because we're not actually at the equivalence point for a color change. We're very close to it. So we call that the end point. So the end point of the titration is based upon the position of the color change. Now, if your pKa for the acid of your buffer is 9.4, then it'll be smack on the color change for phenolphthalein. But what did we say? It was 8 point something for acetic acid. Oops, sorry. Here we go. 8.72 for acetic acid. So phenolphthalein is a pretty good choice. It's very close. This just explains why we get the pH, the color change. For the basic solution, it's pink because this species of phenolphthalein This is due to the color change. This causes the color change here. It's pink because this is now conjugated with these double bonds. Whereas here, when we protonate this one, we produce an aromatic ring here. This is not aromatic. It's aromatic. That means nothing, of course, but it's true. But that's the cause of the color change, because it picks up the proton here, and that changes the color. And all of these acid-base indicators are weak acids. In other words, they behave just like a weak acid. The titration that's going on, they're parallel reactions. Only they're very small amounts, so they don't influence significantly the main reaction that you're interested in, the acid-base reaction. Okay, so this explanation is one where we look at what's the optimal pH range for an indicator. And you have a pK value for the indicator itself. Like I said, they're weak acids, so they have pKa's. So we look at the pKa and we say, all right, how far can we swing on this ratio with the Henderson-Hasselbalch equation before we see a color change? Color changes are due, physiologically speaking, we can pick up a color change if the concentration is tenfold, 10 to 1. So in this case, if this one is 10 times as much as that one, we get a pKa plus 1. If the acid is 10 times the conjugate base, then we get a pKa minus 1. So our color change range is pKa plus or minus 1 pH unit. That's where that comes from. So the phenolphthalein has a usable range between 8.4 and 10.4. And then that's how they calculated these others. These are different. You can't see them on the video probably. But there are a whole host of different color indicators. And these are the color changes. As you move toward the basic, let's see, where's phenolphthalein? Phenolphthalein is here. So here you go from acidic is colorless, and then basic is kind of reddish pink. That's not really accurate. Because when you look at it, it looks pink. And these are other indicators. So really all you have to do is look at, all right, what's the pH at my endpoint, at my equivalence point? And then find an indicator that brackets it, right? If it's going to be 3, then erythrocin B might be a good choice. Or maybe even 2,4-dinitrophenol might work. If your pH change at equivalence is going to be in the neighborhood of closer to 10, then you may want to lose thymolphate instead. Okay. Have you ever seen what they call a universal indicator? It's a solution. It's a mixture of several of these. And it goes through a series of color changes. That's what pH paper does. If you stick it in a solution and it changes a different color and you hold it up against that scale.
Oh, like the full pH tester?
Yeah. Yeah. It's got it has several different indicators in there, so it can watch the pH change over a wider range. And you just have to compare it to your color scale. And it's a combination of several of these. Okay, that's it.